So hello everyone, and welcome to today's lecture recap. So we'll start with a review of what we talked about last time, and that was basically energy in the context of simple harmonic motion. We understood that when you have an oscillating system, you're transferring energy back and forth between kinetic energy and potential energy. But then we also understood that in real oscillating systems, as you learned from a very early age, you typically don't oscillate forever. Instead, some of that energy gets transferred to the environment. And so you see that reflected in the fact that the amplitude for your oscillation doesn't actually remain constant. It gradually slows down, it gradually decreases and goes to zero. And so that, for example, would have been familiar to you on a swing system before you learned how to make the swing go yourself. So in today's lecture, we're going to talk about the kinds of forces that lead to this damped oscillation that we talked about last time. We'll understand where this exponentially decaying oscillation that I wrote down last time actually comes from in terms of the physics. We'll talk a bit about using computer simulations to simulate physics. And then at the end, I'm actually going to talk about the situation where we have a driven oscillation, which is basically how you manage to keep the swing going using your legs. And in general, this is applying some time-dependent force to an oscillating system. And there's some interesting physics there, in particular, the phenomenon of resonance. So just to review our formulas from last time, we talked about a particular kind of a damped oscillation where the amount of energy that you lose is basically a constant fraction of the energy that you have for each period of time. So this is a particular situation that is relatively common and very simple to describe mathematically. So for example, in an oscillator like this, every full period, you would lose the same fraction of your energy or the same fraction of your amplitude. And what we understood is that a damped oscillation like that has an amplitude that decreases exponentially with time. So the amplitude is equal to the original amplitude at time 0 times the exponential of minus t over t0. And t0 was this parameter that we defined by looking at how long it takes for the amplitude to decay to 1 over e times the original amplitude. So that's indicated in this graph here. You look at the original amplitude, you divide that by e, or multiply by 0.368. That's the amplitude that we're looking for. And t0 is then defined to be the time at which the amplitude has fallen to that amount. And because we're losing the same fraction of our energy for each equal time period, if we go up to time 2t0, then our amplitude will have decayed another factor of e. And so the amplitude there is a0 over e squared, or a0 times e to the minus 2. And so that's where this exponential, this general formula comes in. T over t0 is just the number of these time periods. And that tells me the number of factors of e that I need to divide by. And so remember, this is the amplitude of our oscillation. But then to find the displacement as a function of time, we just multiply that thing by the cosine function that describes the oscillation itself. And so then instead of an ordinary cosine that has a non-changing, a constant amplitude, what we find is this oscillating function that has the decreasing amplitude. All right, so I want to give you an example to work out something to do with the damped oscillations. And the thing that we'll often ask you in this situation, given some function as shown, so this is a particular damped oscillator, we want to know how to mathematically describe that. And so your job in this question is to figure out what is this time constant t0. And so there's one way to do it, which is kind of fairly simple, doesn't really require much calculation if you just want to decide which of these multiple choice answers is correct. And then after you think about that, see if you can think of a way which involves the formula where we can find the T0 more precisely. Okay, so pause the video, take a minute to think about that, and then I will discuss it. All right, so let's get it set up here. And so basically what we're going to do is just use the definition of T0. Oh, that one is not working well. So T0 is basically the time when the amplitude A is the initial amplitude divided by E. Okay, so what we're going to do is, what we want to do here is look at our original amplitude. So in this problem, the original amplitude is 8 centimeters. And what we're going to do is then divide that by E. Okay, so A0 divided by E is equal to 8 centimeters over roughly 2.718. And that's approximately equal to 3 centimeters. And so now what I'll do is I'll look on my graph, and we notice that the place where the amplitude is decayed down to close to 3 centimeters, that looks like time equals 7 seconds. Okay, so T0 is then approximately equal to 7 seconds. Okay, so that's basically just by looking at what is the amplitude that we want to that we need to decay to, and then where does that happen on the graph. If we calculated this a little bit more precisely, then it's not quite 3 centimeters. Okay, so this ratio turns out to be, I think it's a little bit less than 3 centimeters. And so this is not giving us a precise value for T0. And so let's think about the situation where we want to maybe figure out what T0 is more precisely. And so what I'm going to do is go back to our specific equation for the amplitude. And what I can do is choose a point on the graphs where we can figure out what the amplitude is very precisely. So we know already that A0 equals 8 centimeters. And if I look on the graph, so it looks like, for example, at time equals 5 seconds, then the amplitude is exactly 4 centimeters. Okay, so we're going to assume that. So at t equals 5 seconds, then A equals 4 centimeters. And so we can go ahead and plug in those values in our equation and then just solve for T0. So let's do that. So we get 4 centimeters equals 8 centimeters times e to the minus 5 seconds divided by T0. And now we just have to do some rearrangements. So dividing through, we find that e to the minus 5 seconds over T0 equals 1/2. And because we want to invert this exponentiation, we need to take the logarithm. So we take the natural logarithm of the left side, and that equals the natural logarithm of the right side. And now we solve for T0. So that's equal to 5 seconds minus 5 seconds over the logarithm of 1/2. Okay, and so I don't have my calculator with me, but that works out to something which is not exactly equal to 7. Okay. There was a question in class. Let me talk about another question that would be similar to this that you might find. So there might be a situation where you have a decaying oscillation. And instead of starting at the top of the oscillation, so instead of an ordinary cosine multiplied by that exponential, maybe we have a phase shift. So maybe we have an oscillation like this. And then you might want to figure out what is T0. And you might also want to figure out what is the original amplitude. Okay, and so in this case, what you notice is that the original amplitude, you can't really see it from the graph because the initial velocity is actually, so the initial displacement is 0. This is at the place where you have the max initial velocity. And it wouldn't be correct to say that this here is the original amplitude because already some time has passed, and so the amplitude will have decayed by that point. Okay, so what would we do in this case? So the way that we can understand this is, first, we could just choose to look at a couple of positions where it is easy to read off the amplitude. So we could choose this time t1 here and read off the amplitude a1, and we could choose that time t2 there and read off the amplitude a2. And then we could just write down our equations that a1 is equal to a0, which we don't know yet, e to the minus t1 over t naught, and a2 is equal to a0 times e to the minus t2 over t naught. Okay, and then we could just plug in our values. So we've got values for a1, a2, and t1 and t2. And so plugging all those in, then it's possible that we can use both of those equations to solve for a0 and solve for t0. So let me just show you one step in that. Okay, so a trick here is to just divide one equation by the other, and that eliminates a0. So say we want to just figure out t0, we can just divide one equation by the other, and then that gives us that a2 divided by a1 is equal to e to the minus, and then it's going to be this difference, t2 minus t1 over t0. So let me just point out that if we do this, so we figure out this ratio between a2 and a1, we figure out the difference t2 and minus t1, and then we solve for t0. So that's exactly what we did before. Okay, so basically one way to think about what we just did there is just that we could just pretend that this is time 0. Okay, so we could just relabel the time and call this time 0. And then we could say, okay, the amplitude from that time to this time, how much time passes t2 minus t1? How much does the amplitude decay by? Decays by this fraction a2 over a1. Okay, so we're just then doing the same thing that we did before, but kind of starting with this time t1 instead of the time t2. Once I have that t0, then I could just go back and use, say, this equation here. Okay, so I do this, I solve for t0, and then I would use, say, the first equation to say that a0 is equal to a1, which I know from the graph, and then e to the t1 over t0, and then that will tell me what a0 is. So, okay, don't worry about it if that seemed a little bit abstract. I didn't really actually use any numbers there. You'll probably see some example of that in the upcoming final homework assignment. Okay, so you'll get some practice doing a slightly more complicated question like that. Okay, so I want to talk about then some of the physics of these forces that would actually lead to damping. And generally speaking, these are forces which exist when they're velocity dependent forces. So they're forces where when the object is moving, it's feeling some kind of a resistance. So it's feeling a force in the opposite direction to its motion. A very familiar example that I'm sure you've seen a lot in high school is the force of friction. And so if I had a mass oscillating on a spring, but then the mass was sliding on a table, then clearly you're going to have a friction force which will be in the opposite direction of the velocity, and then that will end up taking some of your energy away from the motion, and it'll just go into heating up the surface or heating up your object because of that friction. Kind of a similar situation happens when your object is not rubbing against a solid, but just moving through a liquid or a gas. And we would, in general, call those things fluids. So a fluid would be either a liquid or a gas. And in that situation, the kind of friction force that you have is what we call air drag or fluid drag. Okay. And so this is something that's fairly complicated to understand. There's generally not a really simple formula. And the reason is that what happens, say, let's have a look at this oscillator here. So as this oscillates, then the mass is interacting with all the air molecules around it. And generally what happens is it's going to create motion of those air molecules. And sometimes that can be very complicated. So this motion, originally, it's not just heating up the air molecules. Those air molecules are moving collectively. To understand that motion, you need a set of equations that are called the Navier-Stokes equations. You'll probably see them later on in your degree. They're very complicated equations for fluid dynamics. They're very difficult to solve. And usually the way that we understand something like fluid drag is just to do an experiment and observe what forces you have. Or you could try to simulate those fluid motions using a powerful computer. So the net result is that you have a very complicated dependence of your drag force on not only the speed of the object, but also the shape of the object and the specifics of the fluids. But there are a few general things that we can say about this drag force in the fluid. Okay, so we know, number one, that it opposes the velocity. Okay, and so we have this graph it's kind of similar to the graph that we had for restoring forces, except that you have V on the x-axis instead of the displacement. So the drag forces, if you have the velocity in one direction, then your force is going to be in the other direction. If the velocity goes to zero, then the force is also equal to zero. You only have the drag forces or the resistive forces when the thing is moving. And so generally, we're going to expect a graph that looks like this. And like for the restoring forces, the simplest thing to look at would be the vicinity of the origin. So if you have very small velocities, then this graph should look like a straight line. So that's true in the case where your velocity is small. And how small it has to be, it depends on the viscosity of the fluid. So is it like a thick viscous fluid like honey, or is it more like air, or so water would be somewhere in between. Okay, so that's the property of viscosity. The other thing this depends on is how large is your object. So turns out that the velocity of your object, the size of your object, and then the viscosity of the fluid, those three things together will determine whether you're in this regime where the graph looks linear, or whether you're further away where the graph is more complicated. Okay, and so this, the higher velocity situation here, that would say be typical of a medium-sized object like falling through the air. Down here, this would correspond to a slower motion in air or motion in a more viscous fluid. So it's going to be easier for us to analyze this case with the force equals to minus b times the velocity. I'll say a little bit about how you would study a more general case. Okay. So let's think about the case where we have what's called viscous fluid drag. So this is either very small object or very slow or a very viscous fluid. In this case, our damping forces look like this. So it's proportional to the velocity. It's in the opposite direction of the velocity. And then we just have a proportionality constant b, which is coming from the slope of this graph in the previous slide. Okay, so that is just a number that characterizes the drag forces or the damping forces of your fluid. So what we're going to do then is just add that as an extra contribution to Newton's law. And so now we have a restoring force minus kx and this drag force minus bv. And we plug this thing in to Newton's second law in order to get the equation that the acceleration is proportional to this right-hand side. Okay, and so just like last time, we now have a set of equations that can be used to predict the future position and velocity of our oscillator given the position and the velocity now. So again, we have two options. We could try to solve these equations mathematically, or what I'm going to show you in a couple of slides is that we can actually use these equations to simulate the system using a computer. And so it turns out that it's not too hard to actually solve these equations directly. And what you find is that the solution to the equations is exactly this exponentially damped oscillation that I described mathematically in last lecture and in our introduction here. Okay. So here are the equations that we have. This first one is the definition of velocity. The second one is what we get from Newton's second law. What you can do is basically just check that this particular function, the cosine multiplied by a decaying exponential, actually solves these equations. So you check that by first computing the derivative to calculate the velocity, and then you plug that into this formula, calculate another derivative on the left-hand side, and then you can check that the right-hand side will match that if I make the right choice for the parameters in my equation. Okay, so in order to get it all to work, it turns out that I need to choose the t0 parameter, this time constant, to be equal to 2m divided by b, which is the constant that appears in the damping force. And I need to choose omega to have this slightly more complicated form than it did before. So it depends on k and m. There's a square root like we had before, but now I have this extra term subtracted off. So that's a little bit more complicated. One of the things that I'll emphasize later is that most of the time, if you have a damped oscillator where you can see many oscillations before it decays to zero, then we could basically just ignore this second term. It's a very small correction compared to the first term. Okay, but there's another limit where you have very strong damping, where b gets close to this value, 2 times the square root of km. And in that case, this term becomes important. And what you see is that actually when b becomes equal to 2 times the square root of km, this whole thing goes to 0. Okay, and we're going to see what does that mean for our damped oscillation when the frequency goes to 0. Okay, and so I want to show you now basically how we could, instead of solving these equations directly like we did here, how we could instead start from these equations and do a computer simulation that would also help us understand the behavior. Okay, so that's what the subject of this next video is going to be. Okay, let me expand that.
So welcome to this video, which has two purposes. The first is to demonstrate oscillations when the oscillator is in a fluid with viscous drag. And that means that there's a force which is proportional to the velocity of the object, but in the opposite direction, so as to slow it down. The second purpose of the video is to show you how simple computer programs can be used to simulate physical systems. So what we have on this slide is basically just Newton's second law written in a way that emphasizes that we're using the forces to predict acceleration. And then we have the equation which gives us the forces on our system. And so the force includes a spring force and possibly also gravitational force. The combination of those we can write as F equals minus kx, where here x is equal to the position minus the equilibrium position. Okay, so it's like the displacement from equilibrium. But then we also have this viscous drag force, which, as I said, is proportional to the velocity and in the opposite direction to the velocity. Here B is just a coefficient that tells us about how viscous the fluid is. So combining Newton's second law and our equation for the force gives us this equation for the acceleration of our object. And now we're ready to write down these equations at the bottom, which are going to allow us to predict the future motion of our object using the initial position and the initial velocity. And so the way that it works is that if I know the velocity and the position at some time, I can use the first equation, which is just the definition of velocity, to predict the rate of change of my position. So I'll know what my position is going to be in a small amount of time from now. And then I can use the second equation, which is coming from our acceleration equation at the top, and the fact that acceleration is the rate of change of velocity. And we're going to use this equation, given x and v, to predict what the velocity is going to be in a short amount of time, because that's what the rate of change will tell us. So we could try to solve these equations mathematically, and in this simple case, it's possible. But in other cases, it's often not possible to get a nice analytic solution that you can write down, but you still want to understand what is the physics. So let's try to solve these equations, not mathematically, but just using a computer simulation. And I want to show you how that works using a very simple program that I wrote in Scratch, which is very nice because it allows us to do graphical simulations very easily. And so here our oscillator is going to be this brick, which is on some kind of a springy cable. And let's have a look at what our program does. So this part of the program on the right basically just defines the parameters for our system. So I've said that the mass is equal to 1, k is equal to 100, and b, the damping constant, originally I'm going to set that to 0. Okay, so these are in some particular units that I've chosen. On the left is the main part of the program. And so what it says is that when we start the simulation, we're going to set this variable v, so that's our velocity, we'll set that to 0. And we'll set the original x position, and that'll be our vertical position. That's what the computer calls y. So we're going to set that x to be equal to 70. So that means 70, in this case, pixels above the equilibrium position. Now, the third thing we have to choose is something that isn't present in the actual equations. It's the time step that our computer program is going to use in the simulation. And so in the computer program, time doesn't really run continuously. We start out with a position and velocity at some time, and then we predict it at a slightly later time. And that slightly later time is dt. That increment of time is dt. Okay, so once we have our initial parameters set, then what the computer does is it takes the position and the velocity, and then it uses our formula for acceleration to just calculate the acceleration at this particular moment in terms of the position and the velocity. So you'll recognize this first term here is the spring force, and the second term here is the drag force, and both of those are divided by the mass according to Newton's second law. So we calculate the acceleration, and now we just update our position by saying that in this first time step, the position x is going to change by the velocity times the change in time. And the velocity is going to change by the acceleration times the change in time. So we now know the new position and the new velocity, and then we're going to draw the brick here at its new position. It's always going to be at x equals 0, and then we're going to draw it at y equals x. Well, actually x plus 80, I'm just sort of drawing at a slightly higher position on the screen. So I'm kind of defining the equilibrium position to be the 80, y equals 80 on the screen. Okay, so once we've drawn it, then we can go and calculate after the next time step what the new position and what the new velocity are, again by calculating the acceleration and plugging that into this formula. We draw it again, and then we calculate the next position and the next velocity, and we just keep doing that. So let's see how it works. Let's see what it looks like. And so we're going to start in the case where I've set the damping parameter to 0. And so I could start it up at some initial condition where it's above the equilibrium position, and I'll click the flag and we'll see what happens. Okay, and so what we see is that as expected, the brick seems to be oscillating up and down, just like a mass on a spring. And we didn't have any damping, and you can see that the amplitude is basically remaining constant. So I'm going to stop that. And now we can see what happens when we actually set the damping coefficient, this parameter b, to be something non-zero. So let's go ahead and choose that to be 2. We'll try some different values here. And so again, we'll move that up to some initial position above the equilibrium position, and we'll let it go. Okay, and so you can see that it's much different now when we have this viscous drag. The brick started oscillating, but very quickly the amplitude decayed down to 0, and then after not very long, the brick was no longer oscillating at all. We can see what happens if we increase that damping constant even more. So I'll put it up to 10 now. Again, we'll move that up to its starting position. We'll let it go. Okay, and so you see there, I'll show it one more time there. You see there, what happened was that it barely oscillates at all. It went down a little bit below the equilibrium position, oscillated maybe twice, and then it stopped. So that corresponds, you can imagine this thing in some very viscous liquid that would cause it to do that. And then finally, we can set this parameter b to be equal to this special value, which is 2 times the square root of k times m. That's what's called critical damping. And in that case, let's see what happens. So we'll move it up, watch it go. And what we see is that in that case, actually, the brick, it didn't oscillate at all. It fell down through the viscous fluid, and it just settled into the equilibrium position without any oscillation. And so basically that's what the value of damping for which this happens, that's called the critical damping. At any value above that b, we're going to see that, and it's just going to fall down slower and slower and slower. Okay, so in practice, these damped oscillations can be useful, for example, in the shocks of a car, where you want to absorb the bumps that your car might feel from the road, but you don't want your car bouncing up and down a lot, so you want to damp the oscillation. So you have a spring, but also some kind of a viscous fluid that causes that damping. So one of the things I want to emphasize here is that nowhere in this program did we need to put in a cosine function or an exponential function. We didn't need to know how to solve those mathematical equations. The computer is just simulating this system based on Newton's laws themselves and based on our understanding of the form of the force. And we could do a similar simulation in the case where we'd have, say, a v squared here instead of a v. So that would be drag for less viscous fluids. And in that case, it's actually not possible to write down a nice solution for the mathematical equations, but this computer program doesn't care. It'll still do just as good a job with simulating the drag forces in that case. So these computer simulations, they're very powerful, and similar simulations are used all the time in physics and engineering for all sorts of applications.
All right. So here we are back. Okay, so that was the simulation. Really helps you visualize what's going on. Even I think even more than just looking. Even when we had that solution, I think this gives us a nice visualization of, in particular, like what happens as B changes and what this critical damping value is all about, where the frequency goes to 0. So what I have in the next few slides is basically just a summary of what we saw, where I've plotted the actual motion of the brick for the various values that I tried in the simulation. And so the first value was B equals 0, where we had the ordinary oscillation with the amplitude remaining constant. The second value turned out to be 0.1 times the critical value. So critical value in the simulation was B equals 20, and I started out with B equals 2. And so that corresponds to an oscillation where we had many oscillations, but the amplitude decayed relatively quickly. And so that corresponds to this red curve here. One thing we can notice is that the frequency, or the period, it's almost still the same as the original period that we had. And so this is an example where the extra b squared over 4m squared term in the formula for omega can more or less be ignored. Gives you a slightly different period, as you can see here, but it's almost the same. In the next choice, I took b equals 10, which is half of the critical damping value. And there we saw that we only had a couple of oscillations. So it went down and then up a little bit and then back down. And you'll notice here that the time for it to go down to 0, down to the equilibrium position, is actually now kind of significantly greater than it was. And so this is where your frequency formula starts getting significantly modified. And then finally at critical damping, where according to our equation for frequency that goes to 0, what you find is there's just no more oscillation at all. And in that case, we have a pure kind of decaying exponential function. And that's also true as you increase B above the critical value, you get an exponential that just actually decays slower and slower as you increase the value of B. So let me give you one more example here, very similar to the previous question I gave. But in this case, what I'm asking you to find is not the time constant T0, but rather the damping constant B and the spring constant K. And so this would be the other kind of thing that you might be asked on questions about the damped oscillators. So pause the video, take a minute to think about these questions and see if you can work those out. Okay. So let's have a look here. So, okay. So here we go. So there aren't actually any options, but let me work out this thing. So we've got, again, a similar decaying graph. We want to figure out what B is. And so the method here is going to be to use that B is related to our time constant by this equation. Okay, and so now what we'll do is find the time constant in the same way that we did previously. So we find that our original amplitude is 2 centimeters. We find that the original amplitude divided by E, that works out to around, okay, I'm just going to have to guess it. I don't have my calculator here, but let's work it out. 2.7, 2 over 2.7. And so that looks like, I'm just going to say that's approximately equal to 0.8. Okay. And so then we want to look on the graph to see where does the amplitude decay to about 0.8. And so that turns out to be around 8 seconds. Okay, so T0 is approximately equal to 8 seconds. And now we simply use that in our formula here. So we rearrange that to say that B is equal to 2m over T0. And that is approximately equal to, so we've given that the mass is 2 kilograms. So that's 4 kilograms over approximately 8 seconds. And so finally we learn that the damping constant B for this simulation, for this particular graph, is 0.5 kilograms per second. The next part is asking us to figure out what is the spring constant. And there we can make use of this other formula. Okay, so there we can make use of the formula relating the spring constant to the frequency in the case of damped oscillations. Okay, and so as I mentioned, when you see several oscillations like this, so when you see that there are many oscillations before the amplitude decays to 0, that's a situation where you're going to be able to ignore the second term. And so really, we could actually just state that because there are a lot of oscillations visible, B is small enough to ignore in this formula, and we could just calculate K as we would normally calculate it, find the frequency using the period, and then write K equals m omega squared. Okay, but I'm just going to actually work it out in gory detail and show you that it actually is possible to ignore this second term. Okay, so let's actually not ignore it first. And so what we're going to do is rearrange this equation to get an equation for K. Okay, so we get, first let's square the whole thing and multiply by m. So we get m omega squared equals K minus B squared over 4m. So K is equal to m omega squared plus B squared over 4m. And then we can use that omega is 2 pi divided by the period. And from the graph, it looks like the period, so going from time 0 to time 2 there is 1 full period. And so the period is 2 seconds. And so that gives me omega equals pi inverse seconds, okay, or 3.14 inverse seconds. And so then I plug in m, which is 2 kilograms. I plug in omega, which is 3.14 seconds. I plug in b, which is 0.5 kilograms per second, and our mass again. And so I've written those values on this slide here. And so when I plug it in, the m omega squared term ends up giving me 19.2 newtons per meter. The b squared over 4m term, when I plug that in, it gives me 0.03 newtons per meter. And then adding those up, I still get 19.2 newtons per meter if I keep only, say, 3 significant figures. Okay, so this has a small effect, but basically it's not really changing our answer very much. And so the bottom line is that when your graph looks like this, with a lot of oscillations, then you can basically still say that omega is approximately equal to square root of k over m. A situation where you wouldn't be able to assume that would be if your graph looks more like this one, where you only have a couple of oscillations before it settles down, and then your omega might be significantly different than square root of k over m, and then you should use the more complicated formula. All right. Okay, so the last thing I wanted to talk about today is the situation when you have an oscillator and you decide that rather than, so let's get our oscillator. So rather than just letting the oscillator go after some initial displacement and seeing what happens, okay, then sometimes what you want to do is actually, what we say is you drive the oscillator, which means that you apply some periodic force to the oscillator by hand. And so in this case, that would correspond to, say, moving my hand up and down in order to kind of force the oscillator to keep going. And so now the interesting thing here is that I can actually drive the oscillator with whatever frequency I want. So there's a natural frequency that this will oscillate at on its own, but I don't have to drive it at that frequency. Okay, so I could say move my hand up and down periodically much slower, and then the duck will move up and down at that frequency, or I could move my hand up and down much faster than the natural frequency. Oh, it's okay. Ducks can fly. He's okay. Let's put him back on there. Here we go. Okay, hold on tight. Okay, it is possible to do this without a duck, but less fun. Okay. All right, I'll do it without the duck. Okay, so we could make this oscillate up and down. If I sort of jiggle this at a different frequency, then again the mass actually will go up and down at that same frequency that I'm driving it at. Okay, but the amplitude is generally going to be very small. So a very interesting thing is to look at what happens if I drive it with a certain force, and I keep the magnitude of that force the same, but I change the frequency. Okay, so I'm basically going to move my hand up and down sort of first very slowly, and then sort of faster and faster. And then a very interesting thing happens when my frequency that I'm driving it with matches the natural frequency of the spring. I'm not exerting any more force, but you see the amplitude of the oscillation starts to get very, very large. Okay, so even with a very small motion of my hand, what I find is that I end up getting a very large amplitude oscillation just with a little bit of force exerted if I'm using the right driving frequency that matches the natural frequency square root of k over m. Okay, and then once I go significantly above that frequency, then again it just doesn't move around very much. Okay. Okay, so that is the main thing to understand about these driven oscillations. It's kind of like something that you learned as a child on the swings, that you want to basically move your legs in and out and tilt your body at the right frequency. So if you time it right, then your swing is going to keep going with a large amplitude. Okay, so everyone is actually kind of familiar with this. And the phenomenon in general is what we call resonance. So I'll give you a question here just to help you process that. We've got, in this case, a series of objects on springs. They have different masses. And then what we're going to do is turn on this machine that makes the plate go up and down at a particular frequency, which is 1.59 seconds, inverse seconds. Okay, and you want to know which of these masses is going to oscillate with the largest amplitude. So I'll have you think about that for a minute, and then we're going to talk about it. Okay, so let's bring this over here. And now we'll work out this question. Okay, so what we're told is that the driving frequency is equal to 1.59 inverse seconds. And so what we can do is first calculate the angular frequency that we're driving this at. So that's just 2 pi times the regular driving frequency. Let me work that out here on my calculator. So that is 2 times 3.14 times 1.59. Okay, and that works out to almost exactly 10 inverse seconds. And so what we can say with our knowledge of resonance is that the mass that's going to oscillate with a large amplitude is going to be the one where the natural frequency of that oscillator is also equal to 10 inverse seconds. And so we want to set K over M to be equal to 10 inverse seconds. And we're given that all of these springs have a spring constant of 200 newtons per meter. So we get the square root of 200 over M equals 10 inverse seconds, 200 newtons per meter. And then that gives us that M, so we'll square that. M is going to be equal to 200 divided by 100 kilograms. In other words, 2 kilograms. Okay, so the answer for that one is number 2, which is 2 kilograms. Okay, so that's it for today. And that is actually it for our discussion of single oscillators. On Wednesday, we're going to move on and talk about waves, which are also related to oscillators when you have many different parts of a solid or a liquid of a gas all oscillating together in different ways.